Got it. Okay, let me call everybody. But you can be opening your phone. All right, we're going to finish.
Yeah.
We're waiting for a couple of people. We will stop. All right.
I'm just going through, seeing what extra stuff I have.
He's ready for us.
Yeah.
He will give us the presentation also.
Yes. Let me close. Okay. Okay. Are we missing anybody? We will check. Are we missing anybody? No?
Caray
Are we good to start?
Hello again, everybody. Kurt is still with us, and now Kurt is going to share his research. You see the instrument that we saw in the morning towards the management of fruit. In Utah, we have a major crop called cherries. And Kurt, Anderson, myself, and other faculty at the university, we're all working together, looking to develop presentations and farming tools. So Kurt is going to explain to us what he's doing and what are the results he's getting with the sets. All right. Feel free to ask any questions you have, but Kurt, you can start.
Thanks. So this is a presentation I gave as a seminar for our department. It's kind of an overview of what the project is and my part within it. So as Alfonso said, we're working in a crop called tart cherries, and we're trying to map and get as much information as possible so that we can more precisely manage them. So to give a little background on myself, I received a bachelor's from North Carolina State University. I'm originally from the East Coast. And then I did a master's at the University of Tennessee. And I worked mostly in the cotton crop. So in undergrad, I worked in a cotton breeding program. And then in Tennessee, crop physiology, we looked at drought tolerance traits. So kind of the point of showing this slide was that something that you guys may actually be familiar with cotton in Egypt, because they grow a lot there. So cotton's actually a perennial crop, but we treat it as an annual crop. We kind of force it into an annual row cropping system. But now I'm working with an actual perennial crop being tart cherries. So my part of this is kind of working with some of the techniques from an annual cropping system and incorporating them into this orchard setting. And I began my PhD here in 2022. So to give a brief overview of the tart cherry crop in Utah, we're the second largest producing state in the nation behind Michigan. And it's actually our #1 fruit crop in terms of acreage. And it brings into the state about $7 to $21 million US annually. Historically, this crop has been pretty low input, which is represented with that yellow bar. And we've maintained pretty steadily high yields with this low input system. However, in recent years, foreign imports, skyrocketing fertilizer costs, and a persisting drought have put a major strain onto this industry. And so it's caused us to have to increase our input costs while we're not really increasing our yield. So you can see there that profit margin is getting pretty narrow. When we're dealing with this kind of situation, there's kind of two sides of the coin we can do. We can either decrease our input costs, but with a permanent crop like orchards, it's pretty scary for farmers to do. They don't really want to impact the long-term health of their orchard. The other thing we can do is increase our input costs. So really put a lot of money into this crop, but you're not necessarily going to see a high yield return from that. And so with both these options, we're not really solving anything here. So these aren't really the best options. So the goal with our project is to help growers better maintain or better manage their crop to improve their overall efficiency and therefore their profitability. So kind of how I envision this is stretching our inputs and then hopefully either maintaining or increasing our yield to get back to that profit margin that was realized for many, many years. And the tool that we plan to do this with is with precision agriculture. And so what is precision agriculture? It's basically just varying the rate of inputs within a particular field, whether that be fertilizer, water, pesticides. So some of these parts are going to receive less and some are going to receive more. And for this project, I'm going to be mainly focusing on incorporating variable rate fertilizers. And this approach has been used in annual crops for a while, like cotton. And so our goal is to incorporate some of this annual row cropping technology into an orchard setting. And it turns out the tart cherries lend themselves well to precision management for a couple of reasons. The one reason is that they're grown on highly variable landscapes, soil type, elevations, and slopes. They're often grown right on the bench of a mountain. And so this variable landscape lends itself well to variable inputs. Secondly, tart cherries are machine harvested. So we're able to track yields pretty effectively and really get an understanding of what our treatments are doing in terms of yield. And then third, kind of this idea of an orchard history. So these orchards are in production for sometimes up to 30 years. And with that level of orchard history of a single rate application, we run into instances around year 14, 15, we're seeing where with the single rate application of water, nutrients, etc., some of the high vigor areas of the orchard have really big trees, massive canopies, while other areas are struggling. And so within the same orchard block, it doesn't make much sense to continue to do this single rate application and keep building up these trees in the far left corner, while the far right corner, for example, is suffering. To give you an idea of what some of this variability looks like in real life, these are pictures. These are only a few rows apart, and you can see here there's exposed cobble on the ground. This is a very rocky soil. And then about 3 rows over, we have this really nice loam soil with no rocks in it. And when we were actually mapping one of the soils in one of the orchards, the grower was digging this trench. And you can see how rocky it is here. And then down further below, there's no rocks, and it goes to like a silty sand. And this is only within maybe 200 feet. So to give you an idea of where this is all taking place, we're down here in Utah County. Here, we're right here right now, so it's about 2.5 hours. And we're doing this experiment on 4 different orchard blocks, which are named West Ewell, East Gap, 28 Acre, and Huber. And these orchards were chosen for their variability in soils and observed canopy density by growers. So we went out and asked the growers if they have any fields that they noticed variability, and they were like, oh yeah, here are some. So these are the ones that we're working in. To give you an idea of the variability within East Gap, for example, this is an elevation map, and you can see that there's a 68-foot elevation difference between the lowest point, which is around here, and the highest point, which is over here. So this is a very sloped field. Okay, so in order to implement precision inputs, we first need to map the variability within a field, and then we need to adjust our rate of input based on that map. And so the foundation of any variable rate fertilizer program is going to be our soil maps, which is what we worked on today. And this should look familiar to you. This is the same setup we used this morning, but I was using it in an orchard. So here we have our GPS and our probe, and we drag it through the field and geolocate or georeference that information with the GPS. So I explained this a little earlier, but this machine takes 10 measurements per second. So we're able to map a large area at a relatively fast rate. I think this is about a 28 acre, and I'm sorry I'm using all these American units. I can't convert them easily. This field's about 28 to 30 acres, and it took me like two to 3 hours to map the whole field, which is pretty remarkable. And we were able to get really high resolution data. And the reason we've chosen to focus on electrical conductivity is because a lot of papers have supported the idea that a higher electrical conductivity shows as a higher clay percentage. And as we know, if you've taken any soil classes, the amount of clay in your soil has tremendous implication on how we're going to manage that soil. And so the kind of the framework of my part of this project is to create these soil maps, use the soil maps to create our management zones, and then apply variable rate fertilizer prescriptions based on those management zones. Okay, so after we implement all this variable rate technology, et cetera, into our orchards, how are we actually going to measure the changes that are occurring? So we have a variety of ways and a variety of measurements that we plan on taking. One of which is canopy density, canopy volume or shoot elongation, which is a good indication of our nitrogen status, vegetation indices, which is an indication of overall tree health, and then yield. And so to measure our canopy density, we use a technique known as septometry. This is another precision tool that I could have showed you today, but it's basically an ATV, and we have this light bar that we mounted to it, and it measures light. And we also have this sensor that's on the outside of the canopy that's also measuring light, and they're synced up to measure at the same time. And so as we drive through the field, we can divide these values by this value, and it basically tells us how much light is coming through the canopy to the canopy floor where that's driving. For our canopy volume and shoot elongation, we've been talking with a couple of these companies that use LiDAR systems, and we actually just acquired our own LiDAR system to measure this ourselves. And we can drive this through the canopy as well and do side scans to get an idea of our canopy volume and shoot elongation. So this is something coming up in the future that we're excited to do. Vegetation indices, by now you guys probably know all about that, so I won't go into that. And yield, again, I mentioned that cherries are machine harvested. This is a picture of that. And I don't know if Anderson's talked about his yield monitor, but this is involved in this project too. So we can monitor the yield throughout the fields to understand how this is all affecting that, which to the growers is their most important focus. So to give you just a kind of preliminary data on just one field for the sake of time, we'll focus in on a field called West Ewell. And here are some of its stats. It's 23 years old or 22 years old, 23 acres, and etc. So we've managed this, I guess this was last summer, I managed to create a soil map. I got a few canopy density or light penetration maps And we're also collecting a few vegetation indices. And so this is the soil map for this field. So each one of these dots was an EMV value when I drove through the field. So you can see just how high of a resolution we were able to achieve here. And so I drove through each one of these rows, and the EC, which is in millisiemens per meter, ranges from about 7 all the way up to 45. So there's quite a bit of variability. We're seeing this huge pocket here of high EC. And when we interpolate it out, you can kind of see these clear zones emerging that we can use to create our fertilizer plan. This is a canopy density map that was created through that septometry machine that I briefly described. And so these darker areas are where there's more shade, so a higher canopy density, and the lighter areas are where more sunlight's coming through, so a smaller canopy density. And then here's some vegetation indices that Anderson calculated with drone imagery, and also some satellite imagery from Simplot that they provided us. So we're looking at all of these in tandem with each other. And so, yep.
Why millisiemens per meter?
I guess just to make it, just to reduce it by a factor.
I mean, because normally, so millisiemens per meter is SI, which is nice, but normally it's decisiemens per meter or microsiemens per centimeter.
Mm-hmm.
So I was just wondering why millisiemens per meter? It's kind of unconventional.
Was the millisiemens per meter was the SI unit?
So because like decisiemens isn't really an SI unit.
Yeah.
Stay on the orders of 3. But for whatever reason, probably just because of legacy in electrical conductivity, it's always decisiemens per meter or microsiemens per centimeter. So that's what I was wondering why.
Okay. The reason why is because when I did this, I didn't know that stuff.
Okay.
So, but I could definitely go back and change it, but it wouldn't change the range of the values.
It's just going to change it by like 10.
Yeah.
Factor of 10.
These numbers will be different, but the overall range and trends will be the same.
Yeah, it won't change anything.
Okay. That's good to know though, for when this becomes more real, because I should know that stuff. So yeah, thank you.
No worries. That's not a criticism. I was just wondering.
Okay. Yeah, so we have all these maps. This is the same orchard. We have all these maps, all this information. You can kind of see these trends starting to emerge. So this area up here is having the high electrical conductivity. It's also showing a lower canopy density. So there's more light coming through. So these trees are appearing to be weaker. This is also showing up in our NDRE. So it may be a little hard to see, but this is a lighter area. And then also these Simplot satellite imagery that they've provided us, which they call tree vigor. It's basically just, they use their own vegetation indices with their satellite data. And you can see here, this area is showing a lower tree vigor. So this is something we're interested in continuing to pursue to kind of tease out why these things are occurring. And
sorry.
Yeah.
Can you go back? Another question.
Sure.
On your EC map, red is high. Is
Yeah,
right?
That's right.
And blue is low.
Right.
So you would expect a higher clay content in the red.
That's what we expect.
So any thoughts on why that would cause low tree vigor?
That's something we're looking at, and there's a few slides at the end. This trend is actually the opposite in a couple fields. So like our hypothesis would be a higher clay content would have healthier trees. But in this field in particular, the high clay content is showing less healthy trees. And we're not totally sure why that is. We need to go back in and do maybe a few more measurements. But one thing that these maps don't show is that this is a really low point relative to the entire valley. And Utah Lake is like right here. So I think that there may be a water table issue with this. These trees may be like, their roots may be getting too much water and they may be soaked.
So they have wet.
Yeah.
Okay,
And we went in and took soil samples in here, and I can show you those results later, but that area does have really high clay.
Which factor affected the value of the EC?
So there's a couple that can affect it. The literature is basically soil texture,
Yeah.
organic matter, salinity, and moisture.
Uh-huh.
And so we plan on measuring all of those to see what's affecting the EC.
so it'd be anything that affects electrical conductivity, so it'd be electrolytes, charged ions, which would include clay particles with their negative charge, and then water content, which affects the ability of electricity to flow between charged particles. And so clay content and the presence of salts tend to be two big ones. Water content's important. And so a lot of times when you do electrical conductivity surveys, you try to get water contents to be similar, maybe everything at field capacity or something like that, to try to make that less variable. Or you do repeated maps to see what changes from one map to another, so you could look at what effects are static, which would be texture and possibly ion concentrations, and what are dynamic, like soil moisture. One thing people do is they'll correlate the EC to sand, silt, and clay, but there's really only a mechanism for it to be correlated to clay. So if it's correlated to sand, it's usually really just because it's the inverse of clay. It's the real correlation is with clay, not with sand. There's sand particles there's not a reason why they would affect electrical conductivity.
I mean, if we have a map like this, and we know many factors affect the EC, is soil structure or soil type, soil salinity, moisture content, and water table. Can we know from this map which factor it changes the color of the maps?
So the only way to do that is by going in and taking soil samples, which is something we've done.
Uh-huh.
So I can explain that quickly. So all this data I have in an Excel sheet,
Mm-hmm.
and I took the outliers away, and then I broke all that data into percentiles.
Mm-hmm.
So I had a min and a max, and then the percentiles within. And then which within each one of those percentiles, I found the location of it.
Mm-hmm.
And we went in and we soil sampled from that
Yes.
location. And so these blue dots are actually where we soil sampled across the range of the
To
EC.
define which factor affects.
Yeah.
Mhm.
And then we go in and we measure the texture, we measure the salinity, we measure the organic matter, and we see what correlates strongest with the EC. And then we can have a better idea of what's changing it. So yeah, that is an important thing. Like this is just an EC map. Doesn't really tell us that much other than the EC. But we need soil samples to back it up, which is what we did last winter or over the winter. Something else we were looking at doing is correlating our maps within each other or against each other. And so a way to do this, which you guys may be familiar with, is overlaying these fishnets on our soil map and our canopy density map, and then extracting the mean values within each one of those cells. And when we do that for this field in particular, we're seeing a moderate relationship between our soil electroconductivity and our canopy light penetration, which is the septometry. So basically, as our EC is increasing, we're seeing an increase in light penetration, which means that the trees are smaller and have less leaves and aren't as dense. And so what's next? With all of this information, we're going to continue to collect more information. This year, we did this. We established a VR fertilizer system. And this spring, I have been applying our fertilizer treatments. And then for the next couple of years, we're going to monitor the tree growth and see if our variable rate fertilizer can help even out some of this tree vigor within a field. because I should have mentioned this earlier, it's ideal to have uniform tree growth throughout a field for various reasons. So we can continue to measure the relationships between our soil, our tree growth habits, and then our yield. And we'd like to determine how the historical management has affected the cherry orchard ecosystem within each field, looking at things such as irrigation, fertilizer, and pruning. And then ultimately, we'd like to quantify the benefits of establishing this long-term
What do you
tree
mean?
uniformity.
Pruning?
Pruning is cutting branches.
Lean.
Yeah, so there's a lot of research that goes into
Yeah.
how and when and why to cut branches off trees.
Yeah.
And that is basically it. This research is funded from a special crops research initiative by the USDA. And I'll take any questions that you may have. And I can also show you this. This is kind of an extra slide, but these are other fields, our soil maps. This is 28-acre East Gap and Huber. So you can see these nice patterns emerging. And as Burdette brought up earlier, this is a field where the soil is affecting our canopy density in a way that you would predict, where a higher or a lower, a higher electrical conductivity is showing lower light penetration, which means that the trees are bigger and healthier. So that's that.
Good one. Good luck.
What's the current?
I have just one question.
Sure.
I'm curious about the values of EC. The red values are how much, because I can see.
The values were in
Yeah, the
millisiemens
maximum where?
per meter. The maximum here is 43, 44. This is 65, and the maximum here is 40.
And what is the lowest?
The lowest goes 7.6, 17.8, and 10.
This is what, as I mentioned to everybody, these maps, it's what we are looking to incorporate to when we study the data from drones. When we use Landsat, all this data gets blurrier at 30-meter resolution. So Landsat is used mostly for field average, field mean values. But with drones, because we can see individual trees, this data will help us to explain why these areas have a different behavior than other areas. Here, for example, this is very interesting. We have low clay, high, low, high, low, high. And I think there is a geological explanation for this, because all these fields are nearby a lake. And in the past, the lake was much wider, and there were these deposits of clay and sandy. And over time, the field has been leveled, exposing this variability of textures. This is interesting. And one question that I have for my irrigation students is, if you have to design an irrigation system from scratch, brand new field, and you are given these maps, how will you design your drip irrigation system? Which direction the manifold will go?
What do you mean?
How will you design a drip irrigation system if you get this map, and this map?
Yeah. You mean the layout of the drip irrigation
Yes.
system?
What will be the layout?
The layout where is the local of the main line and the
Yes.
manifold
If
and
yes,
the drip line?
yes, that's the question. If you have this soil map
Yeah.
beforehand, before you design the irrigation, how will you design it? Which direction? Which direction your laterals go?
Yeah, but it's depend also the direction of the slope.
Okay.
If we assume the field is level.
Okay, let's assume all
Yeah,
the fields are
that's
level.
okay. You mean wait. The laterals, it
This is for the
means the
certificate
main
for-
line is the same. Wait, okay. I think we speak about the distribution uniformity of the drip irrigation system, because in each color should take the same amount of water, because the same each color has the same soil texture,
Yes.
maybe
Clay versus
right. So I think if you ask me where is the I can
What's the
put
direction of the lateral?
the manifold here,
Okay.
the manifold here, or the main line here,
All right.
and then put the manifold, and then put the lateral.
Okay.
Can maybe, but it's difficult when you have many colors like this.
Okay. That's one design for this one.
Yeah.
Yes.
If you have the slope, if you consider that the land is
Level.
has the same slope,
Yes.
I would put the water to flow from the high density of ET.
Come show us. This is for the certificate. You will need
Where is
that
the diagram?
signature if you don't do it.
It's the easy map is the number one.
Okay.
Number one, number three.
Reach the water from
Number
here to
three.
there.
Yeah,
Okay.
To reach the salinity from
In the
this
middle.
place to the other place. But also some soil amendment would be added, like for example, calcium, calcium sulfate or something like that. So to help reaching the salinity. And also I would ask where is the drainage? Where is the
Okay.
main drain canal? So the design should be going towards the drain.
Yes.
So to reach and to get solve the problem of salinity.
Okay. Yeah. All right. So
I think
The first one is diagonal.
see, this is diagonal.
Yeah.
Okay.
Second one is vertical. Then third one is horizontal.
The third one will be horizontal.
no, I think it's optimum layout for this. The main line come here, and
Okay.
here we put manifold. It's okay for lateral,
Okay.
and it's okay for lateral, and maybe we put here another manifold.
You know why I'm asking you this? Because then here is the problem. First is that excess of water on the root zone for cherries
Yeah.
causes a lot of issues to
Yeah.
the tree itself.
Yeah.
So the farmers could irrigate every day, but this clayish area, as they conserve water, they will be making the plants prone to diseases, and the trunk itself start breaking, I think, right? So what the farmers or what the producers of cherry, they want to know what's the minimum water that I need to put,
Yes.
and if I could rearrange my irrigation system, so these areas where I have low yield, I could increase it.
Yeah.
While this area maintaining the productivity of these low clay areas. So they want, for one, if they have a existing irrigation system, how to operate better the different sections. But if they can start from scratch, from brand new, what will be the new design of that system if you have this soil
But
house?
what is important, he said we should take a soil sample to define which color, the reason of each color.
Yes.
Because maybe he draws this map, and the moisture content is a different between the two sections of the field. It may be.
That is true.
Yeah.
Yeah. And we did ask the growers not to irrigate for like
Yeah.
a week before we took this. So we assume a relatively uniform soil moisture. And then also another thing was temperature.
Yeah.
We take a temperature sample of the
Yes.
soil, which I didn't do in Wellsville, but we should have. Yeah, another thing that goes back to the orchard history. So with the single rate, which also may be a reason why some of these correlations are opposite of one another. So some growers, for example, here will irrigate for the dry spots, they'll irrigate for the sandy, and then some growers will irrigate based on the high clay areas. So they just kind of sacrifice a portion of the field because they have really no other option because they don't have this information.
Mhm.
But if there is a possibility to separate the field to subplots, for example, and if we teach location as for its condition, for example, some subplot for the red area, subplot for the light blue area.
Mhm.
So in the red area, you can, for example, expand the period between irrigations.
Sure.
As it's a clay soil and it can hold the water
Yeah.
for a large amount of time. And also you can, using soil amendments to help to it's kick out the sodium and make calcium
Right.
in, attracted to the soil or absorb it to the soil better than sodium. It will help also to improve the quality and the yield of your of this area.
Yeah.
And also the light blue one, it's a sandy soil or what?
Yes.
It's sandy soil.
Yeah.
So maybe in this case, organic matter or compost can be a good help
Yeah.
to increase water holding capacity, soil water holding capacity, and also reduce the amount between or irrigation intervals. So the period between irrigating this subplot and this subplot maybe not, it may not be the same, but you can also manage it to not to be stored, not be there in the field all the time, irrigating these areas and irrigating it. You can just match the times also for efficiency.
Right.
So you can irrigate this area twice, and every 2 times, for example, you can irrigate this area, depending on the availability of water.
Yeah. Yeah.
You see, there are different ideas on how to deal with this. The question that we have for the project is, which one is the most cost effective? Which solution among the different, like redesign the irrigation system, lay out the subplots and change the timing for every subplot, adding soil additives, organic matter, calcium, etc. Which one is the most cost effective? Because remember, we need to keep the cost down. Yes. To increase the yield profitability. So that's the big question we have. So for right now, we're like just collecting data like crazy. And how many times you go to the field to collect data?
A lot.
Almost every week. We go and map different fields that we have. We fly drones almost every week to try to have enough data that allow us to say, okay, we see these different patterns in the soil. We're seeing that the plant is responding to those patterns. So based on your irrigation systems, maybe the best solution is to keep irrigating this the same, but here reduce or increase the time. Or as you say, maybe for another field could be, look, there is too much variability, but the plot is small enough. So add this soil additive might be your fastest way to keep your same irrigation system, but improve your harvest.
Something also, if we are talking about cost-effective management, so we can also consider the location we are going to apply. For example, in Egypt, calcium sulfate, yeah, is one of the cheapest components. For example, as a soil amendment, I'm not sure of the name, but it's CaSO4, Ca2SO4, .4H2O. So this is one of the cheapest soil amendments in Egypt. But if I go to Ethiopia, for example, and recommend adding calcium sulfate, it will be like crazy because it's as expensive as gold. So
yes,
cost effective is something tricky and different from one location to another. So at the end, when you decide, if you decide to add soil amendment, so you have to be careful about the cost in the area you are deciding. What is going good here in US, for example, may not be valid in Egypt and other places.
One other thing we're looking at this project, and this is Christina's project, is the water retention of the soil is related to the occurrence of diseases. So we have another component in this project where a student is checking the level of infestation of the plants and tracking them over the season. So to see if this spatial information, drone information, can tell us something about the occurrence of diseases or insect affecting the plant. So this project that Kurt and Anderson, myself, and others are working on, it's is looking to this from the agronomical point of view, from the soil science point of view, from the remote sensing part, look into, okay, we have all this data, can we explain what happens in all these different fields with this information, and how we now just condense all that information and give you recommendations about what can be done in order to increase productivity.
And some,
I agree with you because that's case specific. So that based on that we can do like ground truth. So ground truthing, like a quick diagnosis of the field or of each farm. So we see what affects most each plot or each farm, and based on that we can also do this economical analysis, and also try to recommend the agriculture to do one practice or two practice or three practices. For instance, if we have one farm that is closest to the water and the water is kind of almost free, so you just avoid that issue because it's cheap, or you just manage this easily. But maybe this farmer doesn't have I don't know, money to go to pay some manure to increase water, I mean soil structure. So maybe we can, based on that, we can choose our management measures. So I think drones could help us to see what's going on, but to implement in the field, we have to do these ground truths going before to the field in order to balance what could be done first and what degree and then continue. I think only by drone doing that, I don't think it's possible. I think we always have to go to the farm to do some diagnosis.
And that's what's happening in this project, is a combination. Drone or satellite or drone data alone cannot explain the variability. Having this data, the soil variability, it's very important for us, so we can develop relationships and clear understanding what's the impact of this variability on the productivity of the chain.
Because in some cases, it's just enough to improve the drainage and to add soil amendment, and that's it for soil salinity. Sometimes it's just enough without touching the design of the irrigation system. It just improves the drainage. Sometimes in Egypt, in the saline areas, on the surface of the irrigation, we have the drainage system 40 meters space. But sometimes you need to add like 20 meters spacing for drainage. So sometimes we make manual drainage, like more drains. We can add more drains at 20 meter spaces with soil amendment or soil organic matter, increase soil organic matter. And voila, that's it. So sometimes the solution should maybe very simple and cost effective and cheap. And sometimes it's complicated and you have to.
But we should remember the green, the red color is that depend what is the value of EC. Because if we show the 3 red color, all these soil types are not salinity. Because I think that when we want to say this soil is salinity soil, the EC value should, I think, should be more than 1,600. A 160,000 milli per meter. It's depending.
Yeah.
Maybe the red color, but not from the soil salinity. It may be come from the decrease of the amount of the organic matter in the soil.
Yeah.
Not all red color, it means the soil is salinity. We must show what is the value of the EC. It's, for example, if you see the red color, but with 3 value of the EC.
So this is the project we're conducting here on cherries, and one of the interesting things is we have snow. We built a snow pack here. So before Kurt goes to do the mapping, the snow will melt and wash the soil. So pretty much give us like a minimum conditions of salinity before the season, or lower conditions of salinity. So we have high confidence that this is more related with the characteristics of the soil rather with the salinity itself.
Yeah, I can show you the texture data we took. It's really highly correlated with clay percentage. And one of these, I think this field, the R-square value was 0.9 for the 11 points that we took. Percent clay at each one of those points, and then the EC value is very highly correlated. And just one more thing, the approach that I'm using with this is using this information for fertilizing. And so going back to maybe what you talked about with price, we didn't feel comfortable asking the growers to increase their amount or decrease their amount. So what we did is we asked them, like, what would you apply to this field this year if we weren't doing this experiment? And they would say, like, I'd be giving it 200 pounds per acre of this fertilizer, or 400 pounds per acre. And then what we did is we broke, for this field an example, we put this data in just 4 different blocks, actually 3 different blocks. And so these higher areas received that full rate initially, and then no more throughout the season, because the theory is it has high clay, it can handle and hold that nutrition. And then the lower areas with the more sand, or the middle area, we gave it 50% now, 50% later. And then the really sandy areas, we gave 50% now, 25% later, and then 25% later. And so that's kind of our approach to our split application. So we're not like putting 300 pounds here, 200 pounds here, 100 pounds. They're all getting 400 pounds, but just at different amounts at different times. So that was, yeah. So that's how we're using this to change fertility.
Right. Well, thank you, Kurt. Thank you very much for your time.
Yeah.
Thank you. This morning. Okay. All right. So it's noon. It's 12 o'clock. So, sorry, Siri. Okay. All right. So I think we can go now for the break, for the lunch break. We should get together at 2:30.
Yeah.
Okay.
2:30 on that clock.
2:30 on that clock, which is now.
2:30
We'll have more presentations about projects that we are conducting.
Also, can we start early
to move early.
and to move early? It's already difficult.
Yes, we want to leave early.
Okay, at 2.
Yeah, no,
1.5 maybe.
we can start and 1.5, and we go early 1 hour. If you are safe to that.
Yes.
ولا ايه رأيكم؟ Okay.
If that's okay with you, yes, we can do that.
Yes, 1:30 and leave around
1:30.
Yes, 1:30 and we leave at. Oh, yes.
Yeah, this is, so because this is.
Today you're fasting. Today is fasting.
Tomorrow we will leave early in any way. Remember that no water, no eat.
No water.
ليه؟
No water. Wait.
يجيب لنا الحاجة ممكن
يا انا for us. انما بكره قولي له البريد. لا قولي له فين يا مراد؟ انا بتكلم على حاجه ثانيه، بتكلم على المشي. انا والله كلامي كله على انت تمشي بدري. انا ما جبتش سيره الاكل والشرب.
Sure. Yeah.
Because your major is my major.
لا قول يا مراد خلصت.
عايز اقول له اصل حاجه
يا جماعه انا بتكلم
when you convert MS
انما انتوا قولوا له احنا انا بالنسبه لي
Yeah.
yes it's image with the 5 to 1
يا جماعه اللي عايز بريك يقول انا عايز بريك. قولي له يجيب بريك اللي عايز يعمل.
Okay.
Okay. So you can, but in Egypt,
One
we
cent.
have a variation between this. I
And
have
finish.
in my
One
soil
safety,
and
Three
study
safety?
system, I have
Midnight.
Siemens per minute.
Okay.
By Siemens, 200,
Okay.
2,000,
2,000. Yeah, these are like.
I have